Now, when we're doing a proof by contradiction on a conditional statement, we'll have to just be careful about negating that conditional statement. So that's the focus of this section 6.2. So as we've seen before, the negation of the conditional P implies Q is P and not Q. It's really important to remember that this is the negation of P implies Q. So make sure you go back and review that if that seems surprising to you. So then, right, in order to do a proof by contradiction on a conditional statement, I'm going to assume the negation of P implies Q. So I'm going to assume P and not Q. I'm going to deduce some contradiction, C and not C, right? So I'm going to break math, find out something that's wrong here. And then we'll conclude that it's impossible for P implies Q to be false. Therefore, it must be true that P implies Q is true. So the big thing to remember is that when I'm doing a proof by contradiction on a conditional statement, I'm assuming both P, like in a direct proof, and not Q, like in a proof by contradiction. So later we'll talk about sort of these combinations of proof by contradiction, direct proof, and contrapositive. Let's go ahead and see a proof by contradiction for a conditional statement in action. So I'm going to start off. I'm going to say assume for sake of contradiction. If you're doing something like an exam where you're really in that timed setting, just doing shorthand here, some people will write FSOC for sake of contradiction in their proofs, so you can use that if you'd like, but only in that timed, examined, handwritten, less formal setting. When you're typing these out, you should actually write out the words. So assume for sake of contradiction, I'm going to assume the negation of this if. That, so A and B are in Z. A is greater than or equal to 2, and not Q. So A divides B. The negation of an or is an and. A divides B plus 1. All right, so let's actually think about what we're trying to prove here. I'm saying that if A and B are integers, and A is big enough, then A can't divide both B and B plus 1. So either it doesn't divide B or it doesn't divide B plus 1. So a number can't divide an integer plus the integer after it. So I'm saying, okay, assume that you do have a number that can divide both B and B plus 1. And now we're going to sort of see that this leads to a contradiction. So we'll unpack our definitions. So since A divides B, B is equal to A times K for some K and Z. I didn't draw K, so let's fix that. And A divides B plus 1, so B plus 1 is also equal to A. I can't use K here because I already used it for something else, so I'll pick a new letter and I'll use M. Now we need to try to get to some sort of contradiction. So I notice that these are pretty similar to each other. They just differ by 1, which means these two should just differ by 1. So let's actually look at the difference. So subtracting these, what do we get? We get 1 equals AM minus AK. So I'm subtracting the second one from the first one. Well, now I see that here I have a factor of A, right? So 1 is equal to A times M minus K. A is greater than or equal to 2, so A is positive. And 1 is positive, so M minus K is positive. And I can actually solve for A here. To get A is equal to 1 over M minus K. But this M minus K is some positive integer. So 1 over a positive integer has to be less than 1, or equal to if M minus K is equal to 1. But now we have that A is less than or equal to 1, and from before, from our assumption, a is greater than or equal to 2, that gives us a contradiction. It can't be both of those. So since we got to our contradiction, we can conclude that our assumption is false. So therefore, it is not true that both a can be greater than 2 and a can divide both of these. Therefore, if a and b are integers with a greater than or equal to 2, then it must be true that either a doesn't divide b or a doesn't divide b plus 1, which is what we wanted to show. Here's a question for you to think about. So suppose you have 3 integers, a, b, and c, and we have a Pythagorean triple. So we have a squared plus b squared is equal to c squared. So I want you to show if a squared plus b squared is equal to c squared, then either a or b is even. So as you're doing this, right, do the proof by contradiction. At some point when you need to know what to do next, think about if a is, or if c is either even or odd, and see if you can get any contradiction based on that. So it's kind of similar to the proof that square root of 2 is irrational. Let's do one more proof here. So here I want to prove every non-zero rational number can be written as the product of 2, it should say irrational numbers. So any non-zero rational can be written as the product of 2 irrationals. So the only number I know for sure that's irrational right now is the square root of 2. So given some non-zero rational number a, I want to write it as some irrational, so maybe square root of 2, times some other irrational. Well, I know that a is equal to square root of 2 times, I need to get rid of that square root of 2 and plug in an a. So if I can show that a over the square root of 2 is irrational, then I can just say that a is equal to square root of 2 times a over square root of 2. So that's the product of 2 irrational numbers. All right, when I'm trying to show it can be written as, that's helpful to be able to actually show exactly how to write it as that. But I need this lemma first. I need this little mini proof that if a is a non-zero rational number, so I'll say that is in Q not equal to 0. Or maybe I can say if a is in Q and a is not equal to 0 to make that more explicit. Then I want to show that a divided by the square root of 2 is irrational. So now I can ask myself, how can I go about proving this lemma? So I don't want to do a direct proof because proving things are irrational is hard. It's a lot easier to prove they're rational. So I either want to do a contrapositive or a contradiction. If I'm just going to do a contrapositive, I can only assume that a over square root of 2 is rational. I can't assume that a is rational, but I might want to be able to use the fact that a is rational in my proof. So if I do a proof by contradiction, I'm allowed to assume both that a is rational and a over square root of 2 is rational. And I like to be able to assume things are rational, so that seems like the best way forward. So I'm assuming that a is rational and a over square root of 2 is rational. And again, that's for sake of contradiction. So since a over square root of 2 is rational, let's deal with that first. So a over root 2 is some, we'll say p over q, where p and q are in Z. And let's see if I can then solve for square root of 2, because I know something about square root of 2 already. I know that it's irrational. Then square root of 2 is equal to, just dividing things over, a times q over p, where I know p and q are in Z, but I don't know about a, right? A I've just assumed is in q. But since A is in Q, and maybe we can go ahead and pop that back up here, A is equal to M over N, where M and N are in Z. Maybe I'll put it an N not equal to 0 and a Q not equal to 0. So then I'll plug that in. All right, so I'm just sort of updating my proof as I go. This is the way we want to think about these. So that A is M over N, and I'm multiplying that by Q over P. So that's equal to MQ over NP. Now I know that the N is not equal to 0. But how do I know that that P is not equal to 0? Well, P would only be 0 if this number was 0. But I know that A is not equal to 0 by my assumption, right? So I sort of put that in here as well. A not equal to 0. So then here I have P not equal to 0. Oops. P not equal to 0. Where here I have N and P are not equal to 0. All right, thus square root of 2 is equal to MQ, which is an integer, over NP, which is an integer, where MQ and P are in C, and NP is not equal to 0. But that's a contradiction since square root of 2 is irrational. Thus, the assumption that we made at the beginning must have been false. So what did I assume? I assumed my if-then was false. So I assumed the if and the negation. Thus, it must be true that my if-then is true. So thus, if A is in Q and A is not equal to 0, then A over 2, root 2, is irrational. Now, that was a pretty great proof, but remember, that's just our lemma. That's just this extra little statement that we needed in order to prove our big statement. So now I can go back to the proof of that proposition. Let's go ahead and rewrite this as a conditional. So if A is in Q, A not equal to 0, then A equals, say, B times C, where B and C are irrational. So for this, I'm going to actually do a direct proof. So I'm going to assume A is in Q and A is not equal to 0. I need to show that it can be written as the product of two numbers. So then A is equal to square root of 2 times A over square root of 2, where root 2 is irrational. I'll use the symbol for irrational. And A over root 2, I don't really like that symbol. I'm going to use this symbol for irrational, R minus Q. And that's what I needed to show. So really all of the meat of this work was in our lemma here. So I used a proof by contradiction for the lemma, and then I used a direct proof. So you can read more about combining these different proof techniques in section 6.3.